Hey folks, Sebastian from Madrigal here. This is the main menu for Traction Point, a game I'm developing using my own tools and game engine called Basis. The game is still in development, so the visuals aren't final yet, but it's getting there. For the longest time, I wanted to have some movement in the background of the menu, and now you can see scenes from the game being shown, along with some camera movement. At first glance, it might look like the game is running in the background of the menu, but that is not the case. No level is loaded when the game is in the main menu. Instead, I recorded a few pieces of gameplay, put those together into a video, and made the game play the video in the background of the menu. Sounds simple, right? The thing is, playing video in a game can be somewhat complicated. Third-party game engines often come with a video playback solution built right in. But as I already mentioned, I'm working with my own engine here. There are free open source libraries for playing videos, such as libavif. However, these typically depend on external libraries for the encoding and decoding of the data. Now, I don't have a problem with third-party libraries per se, I use a lot of them actually. It's just that in this case, I simply want to play a video clip in the background of a menu. The video player doesn't even need to support sound. For this, I would like to avoid dependencies on third-party libraries. For Traction Point, I wanted something simpler, and so I set out to build a very simple codec for video files, plus a playback system for the engine. Actually, I built two codecs, or 1.5. You'll see when we get to them. And while at it, I built a custom solution for recording video of my game as well. The result of all this is what you see in the background right now. In this video, we're going to look at the overall structure of the system, and then we'll deep dive into the custom video recorder. In the next video, we'll continue where we left off and look at the custom codecs and playback system. So make sure to subscribe so you don't miss the second part. First though, I need to make one thing clear. My goal with the system is to keep the runtime code, the decoder and video player, as simple as possible. This comes with some downsides, namely inferior video quality and larger video files compared to the state of the art. For example, codecs like H.264. That's not to say the results are bad though. In fact, they're quite good. Having said all this, if you want to implement a truly efficient video codec, there are other better resources available on the internet. But if all you need is basic playback with the least amount of complexity, this is one way to do it. First, let's establish what we're talking about here. What do we mean when we say video clip? In the simplest terms, a video clip is just a sequence of image files. I'm purposefully leaving out the audio side of things, as I play audio separately from the video. However, almost all video formats support sound in one form or another. The most basic video playback system imaginable would simply load and display one image file after another, at some fixed frame rate. For example, 24 or 30 frames per second. So in theory, a video file could simply contain as many images as we have frames in the video. This, however, isn't practical in most cases, as images, especially the kind that GPUs like to work with, contain so much data. How much, you say? Well, let's do the math. At a resolution of 920 by 1080, also known as 1080p, we have 2,073,600 pixels in every frame. Since we will be displaying the video in a game, we will essentially be working with textures that we send to the GPU to show on the screen. A typical texture format for this is 32-bit RGBA, where each pixel occupies 4 bytes of data. To store as little data as possible in the video file, we can discard the alpha channel and work with 24-bit pixels instead, saving 1 byte per pixel. With this format, each uncompressed frame in our video takes up 6,220,800 bytes, which is almost 6 megabytes every frame. That would mean 178 megabytes per second if the video frame rate was 30. So yes, uncompressed video is large, like impractically large. With all of this in mind, it's no surprise that the main job of basically every video codec is to compress the data, preferably without making the image quality suffer. Now that we know what we're dealing with, it's time to make a plan for the new video system. Typically you need at least the following components in a system like this. the video encoder, which takes the raw video input and stores it in a format small enough to be shipped with the game, which we will call the encoded data. The video decoder, which reads the encoded data and converts it into video frames, in other words, images. And the video player, which uses the decoder to display the video output at the correct frame rate. For Traction Point, however, it became apparent that I need a fourth piece to complete the system, a video capturer or a recorder. The recorder is implemented as part of the game engine's renderer, and it allows me to record footage of the game as it is running. To make the encoding process as simple and flexible as possible, I decided that the input to the encoder would be a sequence of image files. In other words, each video frame would be stored in its own PNG file. You might be wondering, why can't I just use an existing video recording tool to record the game and feed the resulting video to my own encoder? Well, if I want to implement my own codec, I pretty much need to start from raw frames. So that would require me to decode the input video first. Plus, storing the frames as individual files gives me a lot of power and flexibility. I could, in theory, record the game using an existing tool and later convert the video into image files. But by that time, the content will already have been encoded in some typically lossy format, and I want the individual frames to be raw image data, stored in a lossless format. Basically, the exact contents of the game window at the frame it was recorded. My reasoning is that since my own video format isn't going to be the best, I at least want the input to my encoder to be of the best possible quality. Then I can do my best to keep the quality around, while lowering the video file size as much as possible. With a plan in place, I started working on the video recorder. That way, when I get to the encoding part, in other words, the really complicated part, I would have a way to easily produce testing data. Writing the recorder turned out to be quite a bit more difficult than I originally thought, though. Remember earlier when we talked about raw image data being large? If 30 frames at 1080p resolution takes around 178 megabytes, then 60 frames takes 356 megabytes. It's completely reasonable to want to record video at 60 fps 1080p resolution. I might even want to go higher than that and record at 4K resolution or something. However, it's not reasonable to expect the game to write 356 megabytes or more to disk per second. Even if I was an expert at I/O programming and managed to write the code so that the capturing didn't slow down the game at all, which in itself would be quite the achievement, we are fast approaching the limits of our storage devices here. I know that theoretical write speeds for high-end disks are higher than that, but in practice it becomes very difficult to achieve these levels of throughput. You also cannot expect to keep the whole video in memory while recording, since the data reaches 1 gigabyte in less than 3 seconds. In order to deal with these challenges, I had to come up with a whole video data recording pipeline. Let's start from the beginning and look at one phase at a time. How can we capture the frames of the game without slowing it down? After all, you don't want the gameplay to be suffering from frame rate drops while recording. As I was working on the recorder, I realized that I actually didn't have a system for capturing the contents of the game window in the Basis engine, so I had to make one from scratch. The texture holding the current image in a video game is typically called the back buffer. It's a regular texture much like any other one, and we can copy the data out of it at any point during the frame. For this system, I set up 2 points for capturing. Right before the 2D pass, in other words, only the 3D contents without any overlays or menus. And at the end of the frame, in other words, the full frame with all the render contents. This way, if we want to capture just the 3D scene, like in the case of the main menu video, we can leave out any UI elements from the video by using the pre-2D pass to capture the back buffer. There is a problem though. The back buffer is typically not readable by the CPU. To work around this, we create something called a readback buffer, which is a texture that the CPU can read from. Whenever the capturing system wants to record a frame, it schedules a copy from the back buffer to the readback buffer on the GPU. The readback buffer can then be read by the CPU. However, even this is not enough, because the GPU works on a different timeline than the CPU. Because of this, the data in the readback buffer won't be available until later. The way to handle this is to have a few readback buffers, in my case 3, set up in a ring buffer configuration. The first time the recorder wants to capture a frame, the back buffer is scheduled to be copied to readback buffer 0. The user, in this case the video recorder, can then ask the renderer if the copy has been carried out by the GPU. And until that happens, it has to keep asking for the frame data. While the recorder is waiting for the frame data, the next frame can already be started, and the recorder asks for a copy of that frame too. This frame would be scheduled to be copied to readback buffer 1, and so on. With a system like this, the CPU is never waiting for the GPU to finish the copy, and the GPU is never waiting for the CPU to read the data back, and the frame rate is affected very little or not at all. We now have a way to get the image data into CPU memory. The back buffer stores the data in 32-bit RGBA format, and so in 1080p resolution each frame occupies a little less than 8 megabytes. By the way, as a side note, this is not the buffer the 3D contents are rendered to. That buffer stores data in a floating point format. The way the recorder works is, you tell it whether or not you want to capture a single frame, in other words a screenshot, or a sequence of frames, a video, and whether or not you want the full frame or only the 3D contents. If you want a single frame, the system captures the back buffer to readback buffer 0 and waits for the data to be available. Once it is, it writes the data to disk in PNG format. Capturing a single frame is easy. The complexity begins when you ask for a sequence of frames. The recorder starts requesting frames from the back buffer and keeps track of their status, in other words, whether or not the data is ready. Once it is, the frame data is written to something called a frame sequence buffer, or FSB. The FSB is simply a buffer large enough to hold a few frames of image data. In my case, the FSB is 128 megabytes, so it can hold 16 frames when recording in 1080p. In addition to this, the FSB also has some metadata about the frames it holds, such as the index of the first frame in the buffer. The recorder has 3 FSBs, in a ring buffer configuration. As soon as the data for a frame is available, it is copied into the currently active FSB. When the FSB gets full, 16 frames later, the data in the FSB is sent to the next part in the pipeline, the compressor, and the FSB is emptied so that it can be reused for later frames. All of this logic runs on the main thread of the game, so it needs to be fast, otherwise it will slow down the game. We already briefly mentioned the next phase, the compressor. This component, which runs in a background thread, is responsible for receiving the FSBs produced by the recorder and compressing the data enough so that it can be temporarily stored on disk during the capturing process. When an FSB is full, the data is copied out of it and into a list managed by the compressor. We call this the input queue. However, the compressor might be busy compressing a previous FSB, so this copying is done using the Basis Engine's job system. Remember, we cannot block the main thread. However, since each FSB can store up to 16 frames, and we have 3 of them, we have 32 frames worth of time to copy the data out of the ring buffer before the main thread starts poking at it again. Recording higher resolutions might require us to have more than 3 FSBs in the ring buffer to give the system enough time to copy the data to compressor-managed memory, though at least 1440p seems to work fine with just 3. The compressor takes one FSB from the input queue at a time and compresses it. Here we're using the LZ4 compression algorithm, which is famous for being fast. This is important because the game will continue to produce data for the compressor at the frame rate the game is running at, and the compressor will have to keep this data in memory until it can get written to disk. Once an FSB has been compressed, it is put into another list, which we call the output queue, from where it will get picked up by the next part of the pipeline, the writer. The compressor then starts compressing the next FSB in the input queue. The next phase in the pipeline, the writer, is reasonably simple. It also runs on its own thread, and simply checks the compressor's output queue for data to write to disk. Remember, these are not individual frame images yet. They are compressed buffers of 16 RGBA8 raw images, or fewer if higher resolutions than 1080p are used. The writer pops an FSB from the queue and writes it to disk in a custom format. It puts a small header containing the first frame index, the frame size, and the frame count into the data. These files are temporary. The only reason we write the data to disk at this point is to avoid having to keep all of the recorded frames in memory. Once the FSB has been written to disk, the writer goes back and pops the next FSB from the compressor's output queue. If the game produces content at a higher rate than the compressor and writer can process, it means that the number of FSBs in the compressor increases. If the compression itself is slow, then the compressor's input queue will grow. And if the writing to disk is slow, then the compressor's output queue will grow. The total number of items in the compressor's queues is called the compressor occupancy. Since each uncompressed FSB comes in at a hefty 128 megabytes, it means we want to keep as few of them in memory as we possibly can. However, the compressor will dynamically allocate more memory if needed, so temporary slowness in the later stages of the pipeline isn't usually a problem. The occupancy and total memory usage of the compressor can be monitored during the capturing process. The final phase of the recording process is called the processing phase. When the recording is stopped, the recorder will send the last, often half-full FSB to the compressor, and the system will wait until the compressor and writer has finished their work. After that, the recorder will open up each of the temporary files in order, extract the compressed image data, and write the final frame images to disk, typically in PNG format. Once the frames have been written, the temporary files are deleted. We now have a folder of standard PNG image files, each representing a frame in our video. These files can be given to the video encoder right away, or we can edit or modify them as we want. Most video editing software support reading image sequences, so we can also encode a standard video of the captured content if we want to. Alright, let's end this part with a little bit of a live demonstration of the recorder here. So, we are in the game, and I'll quickly show you something in the code here. We are in the client in-game state.zig file, and we're listening to the raw input key pressed message. So we have two cases. Basically, the minus key on the numpad takes a screenshot, either a pre-2D screenshot or a full frame screenshot. And the plus key toggles the frame sequence recording or capturing on and off. And there are a couple of new interesting parameters here. First of all, you need to tell the capturer whether or not it should render the debug info to the screen. If we are recording full frames, you might want to turn that off. Otherwise, you get the debug info in the video, which is probably not something you want. And then we have the interval, which is currently set to 2, so this means that we capture every other frame. And that can be very handy if you want to, for example, you want to run the game at 60 FPS but create a 30 FPS video. Then you only need every second frame. And here we are capturing pre-2D frames currently. So let's try this out. I'm going to take a few screenshots. So Control minus, this should give us a pre-2D screenshot. And Alt minus should give us a full frame screenshot. Let's see if we got that. Right, so there's the pre 2D screenshot and then the full frame screenshot. Basically, you can just see these debug menus and text here, as we don't really have any HUD to speak of. But of course, the interesting part here is the sequence recording. So let's start that now, and you can see here the compressor occupancy is slowly going up, typically. And I can toggle it off like so. And now that it's been toggled off, you can see the occupancy slowly going down as the compressor and writer is working to write the last temporary files. Here we can see the temporary files being created. We have 28 of them. And now we've actually entered the processing phase, which means that they will go away now because it will start outputting the final frames here. Ooh, I got 2 of those actually. Oh no, that was the previous one. Let's open this one. So here we have the actual frames, and since these are individual image files, you can actually kind of preview this video almost right here in in the image previewer in Windows. Outputting the files can take a little while because the Windows file system isn't particularly optimized for the case where you have lots of threads writing small files to the same folder at the same time. And of course, also encoding things as PNG takes a while. But yes, the processing is done. We got 448 items. And these are combined 1.14 gigabytes. So this isn't quite 8 megabytes now, it's 2.66, but that's of course the PNG compression. So if we were to save these as something like BMP, then that would be closer to 8 megabytes per frame. That's the recorder. In the next video we will dive right into the whole codec business and see how we can actually take this information, compress it down, and then play it back. So I hope to see you there. Be sure to check back for that video, or if you'd like, hit that subscribe button and all the bells and whistles and whatever YouTube wants you to press now to get notified. With that, I thank you for your time. I hope to see you in the next part. Take care. Bye.